Is the expansion of the universe a lie? Some open-minded scientists are now answering this question in a completely new way. We could be living in a vast void that could solve the mystery of the alleged expansion of the universe forever. This void could even provide us with information about the blueprint and reasons for the existence of the entire universe. But what exactly is this void, and how did scientists come up with the idea that the universe is expanding? The rate at which the universe is expanding is one of the greatest mysteries of cosmology among experts. This expansion rate is expressed by the Hubble constant, h. We know Hubble from the well-known space telescope, but what many people don't know is that Edwin Hubble, who gave it its name, was one of the astronomers who came up with the idea of the expansion of the universe through certain observations. In 1929, Hubble observed the movement of galaxies, and today the Hubble constant is a measure of how fast the universe is expanding, expressed in km per second per megaparsec. 1 megaparsec corresponds to around 3.26 million light-years. Hubble's original estimate for h was around 500 kilometers per second per megaparsec, but this figure has since been revised several times. Modern estimates are in the range of around 67 to 74 kilometers per second per megaparsec. These new estimates are based on various methods, including observations of type 1a supernovae, Cepheid variables, and the cosmic microwave background. The microwave background is actually a key source for determining the Hubble constant. The radiation is thought to be the faint glow left over from the Big Bang. Thanks to the European Space Agency's Planck satellite, we have a very precise map of the cosmic microwave background, and in it, a Hubble constant of about 67.4 kilometers per second per megaparsec could be read. The radiation also shows very clear evidence of the universe drifting apart. The cosmic microwave background is therefore cited as one of the main pillars of the expanding universe theory. Observations of type 1a supernovae, especially with the Hubble Space Telescope, have led to even higher estimates of about 74 kilometers per second per megaparsec. These supernovae, also known in science as standard candles, have a known absolute brightness that allows astronomers to measure their distances and thus calculate the expansion rate of the universe. The significant difference between these two measurements lies in the age of the source. The cosmic background radiation originates from the early universe. Supernovae are recent events. The difference is what astronomers and astrophysicists refer to as the Hubble tension, and this discrepancy raises legitimate questions about our understanding of cosmic history and our underlying physical theories. Some scientists have suggested that an entirely new physics may be necessary to resolve this tension. These include theories that go beyond the standard model of particle physics and include the existence of exotic forms of dark energy or modifications of gravity. Is the assumption of expansion wrong? What if I told you that the whole Hubble constant could be wrong? Because there are observations that contradict the standard assumptions. One example is the discovery of the massive galaxy cluster El Gordo, which appears so early in the cosmic timetable and is so massive that it cannot be consistent with the standard model of cosmology at all. Such observations suggest that some aspects of the universe may be quite different from what we have previously imagined. Observations of the large-scale structure of the universe add further dimensions to the problem. Clusters of galaxies and superclusters appear to be distributed in the cosmos in a way that does not quite fit with the current understanding of expansion. There is an urgent need for clarification here. In particular, we need to find ways to clarify the role of mysterious dark matter and dark energy. The expansion of the universe normally causes galaxies to move away from each other. Hubble's law teaches us that the further away they are from us, the faster they move. The speed at which a galaxy moves away from us is proportional to its distance from us, which means that the universe is expanding equally in all directions. However, this uniform expansion could not be proven and observed everywhere in the universe. It could be that there are other structures in the cosmos that accelerate or slow down the expansion regionally. Another interesting aspect of galaxy motions is the discovery of anomalies that cannot be fully explained by the gravitational effect of visible matter. For example, the outer parts of spiral galaxies rotate faster than the mass of the visible stars and gas clouds with conventional physical parameters would lead us to expect. Among other things, this phenomenon led to the assumption of the existence of dark matter. Dark energy is said to be the mysterious force responsible for the accelerated expansion of the universe. However, we currently know very little about dark energy and dark matter, and the existence of both has not yet been proven. Does Euclid have the answer? The Euclid mission is an ambitious project by the European Space Agency, ESA, and aims to finally shed light on the universe. The brand new space telescope has been in operation since fall 2023 and is surveying the universe once again. Euclid will scan everything we can see so far from the universe and compile it into a gigantic map of the sky. This map should help us to understand galaxy movements and the expansion of the universe, and also solve the mystery of dark matter. Named after the ancient Greek mathematician Euclid, this telescope is specially designed to display many stars in a clearly arranged space and to understand the movements and dynamics of invisible space. The motions of galaxies are a fascinating field of research that will not only expand our understanding of the expansion of the universe but can also clarify urgent questions about the nature of matter, energy, and the fundamental laws of physics. Are we living in a huge void? You are quite rightly wondering what this has to do with the question of whether we might be living in a giant void. This intriguing idea could play a key role in solving some of cosmology's greatest mysteries. Imagine that our part of the universe has a lower than average density, a kind of cosmic void that affects measurements of the rate of expansion of the universe. Other parts of the universe could be denser, and galaxies move quite differently there. This hypothesis could help to explain some of the discrepancies in relation to the Hubble constant and the movements of galaxies. The theory that we live in a vast void offers a possible explanation for this tension. In such a scenario, the local density of matter would naturally affect the measurements of the expansion rate, as the gravitational forces in such a void would act differently than in denser regions of the universe. Scientists further hypothesized that there could be outflows of matter flowing out of the void into other regions due to the gravitational pull of denser surrounding regions, and this could also contribute to an apparent acceleration of the local expansion rate. Interestingly, direct counting of galaxies in different regions suggests that we actually live in such a local void. This void would not be completely empty, of course, but it would have a density of about 20% lower than the average of the universe, and it would extend to a radius of about 1 billion light-years. To test this hypothesis, modified Newtonian dynamics, MOND, or M for short, was one of the methods used. M is an alternative theory to dark matter and was originally proposed to explain anomalies in the rotational velocities of galaxies. In a MOND universe, structures such as galaxy clusters grow faster, and the local expansion rate also varies. New observations of galaxy motions, in particular the so-called bulk flow, which measures the average speed of matter in a given sphere, have provided remarkable results. These observations show that the bulk flow at a scale of 1 billion light-years is 4 times faster than expected by the standard model and increases with the size of the region under consideration. This is in contrast to the predictions of the standard model and further supports the assumption of a local void in which our Milky Way is consequently also located. How does emptiness affect life on Earth? Are you wondering whether this has any effect on our galaxy and our life on Earth? First of all, the existence of such a void around us could explain why our galaxy and its neighbors behave the way they do. In a universe pervaded by such voids, the gravitational forces and the dynamics of galaxy motions could be different from what scientists have understood so far. All in all, this hypothesis would mean that our galaxy and all neighboring galaxies are floating in a kind of cosmic bubble that is different from denser regions of the universe. This void could also have an impact on the development and fate of our galaxy. In a region with a lower density, collisions and interactions with other galaxies could be less frequent, which, of course, influences the long-term development of the Milky Way. These correlations could have an impact on star formation, the distribution of gas and dark matter, and the formation of structures within the Milky Way. At the moment, the void certainly has no influence of any significance on us on Earth. For us, scientists, the discovery of this possibility is a big deal, and possibly school and textbooks will be changed. But you and I don't notice any of this in our everyday lives. However, the assumption of life in a void is interesting in another respect. If our galaxy is located in a less dense region of the universe, this could mean that the conditions for life as we know it are very different here than in other parts of the universe. There are scientists who believe that we live in a part of the universe that is very sparsely populated, which is why we have not been able to find other forms of life. Perhaps the conditions in other regions are different, and there are several planets within a solar system that are inhabited or entire star systems that are densely populated. Such ideas are exciting and could influence our search for life. The hypothesis of a local void will certainly also change our idea of the future of the universe. If the expansion rate of the universe is locally influenced by such a void, this could mean that the future of the universe is more complex than we have previously assumed. Scientists believe that the expansion must inevitably end at some point in one of three scenarios: either the universe freezes because it can no longer expand any further, it freezes, or it suddenly contracts again like a rubber band. If we have regions with different expansion rates, these scenarios no longer fit, and these regions may even balance each other out in a way that we have not yet understood. Last but not least, we must of course also consider the possibility that there was no single starting point from which the universe began to expand. There are serious theories that say that there could have been several starting points or that the universe feeds itself from different sources, like an eternal whirlpool.